Lab 3, Magnetic Dipole Field. In this lab, we will be analyzing the magnetic dipole field and moment of a magnet using our phones by the Teslameter app. As an introduction, the concepts we will be using is the Biot-Savart law, along with our experiment of the Teslameter measurements due to a magnet, and we will have our results and calculations for the magnetic field due to said magnet, and we will also make a glow script model and visualization. For our concepts, we will be using the Biot-Savart law, which describes the magnetic field that has multiple forms for different objects. In this lab, we will be focusing on the distance dependence as described as the magnitude of the magnetic field of a bar magnet is equal to KRN. For our experiment, we first aligned our phone to magnetic north. Next, we found the location of the magnometer chip as shown in the diagram. Then we took measurements for specific magnetic field strengths in the x direction and found our distance for said measurements. And the last thing we did was we took a 45-degree measurement to find the magnitude of our magnetic field. Notice that in our first conditions that we actually had to align our device to point towards magnetic north so that our x component of our field zeroed out to not cause any discrepancies. Here are our results. On the right side of the chart, we have the different strengths for our x direction, as noted as R20, R70, 120, etc. And we have the distance to reach these strengths, and we have our strengths itself on the second columns, and we have these averaged out. These were taken on axis of our magnometer chip, and on the bottom we have the off-axis field, which was the 45-degree angle measurements. We have our perpendicular. We have our perpendicular measurements, and we also found the x, y, and z components of our magnetic field. And with this, we were able to create a graph that shows our ln of the magnetic field in the x direction versus our ln of r. And notice that we can create a linear slope, which will be used in the second portion. For our calculations, we will be using the formula introduced in the beginning with the magnetic field of a bar magnet to KRN. By doing a little bit of algebra, we can isolate our variables, which gave us our graph to the right, and our slope of the said graph is our distance dependence n, which, if we look back to the graph, we have a approximately -3 distance dependence. Solving a little bit further and assuming that our r is equal to 1 meter, we are able to isolate our k, and relating back to the original functions, we have that our ln of k is equal to -0.6, and we are able to find our specific k value and then plug this back in to the formula to find our magnetic dipole moment, mu, which is 2.5 amperes meters squared. For our glow script code, we first begin by creating a function for our magnetic field in the x, y, and z direction. Then we create different arrow visualizations for our on-axis and off-axis magnetic fields. To the right, we have the on-axis and then off-axis arrows coded, and essentially we fill in just a little bit of information for our set distance that will generate a model for us. For our visualization, here we have the bar magnet along with the arrows that represent the magnetic field that is off-axis, which is represented by our blue arrows, and our on-axis by our orange arrows. We also have the 45-degree magnetic field as represented by our magenta arrow. And by doing this, we have our distance d, which calculated the magnetic field. The magnetic field shown on the bottom. For questions, what if you hadn't oriented your experiment to compensate for magnetic north? Instead, laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field. How would your results have changed? This would cause a discrepancy in our x value because originally we zeroed out our x value for the experiment, so the strength wouldn't be correct. As we did the experiment, we found out the magnitude of each component increases as we decrease our distance. So this would definitely change the x component. Well, may not have such an effect on our y and z components, but will definitely throw off the calculations. And what if you were to stick the two identical magnets together end to end and run the experiment again? How would you expect the measurements to differ? Well, with this, we would probably expect that our magnetic dipole moment would increase in its strength and thus have a stronger magnitude in our calculations, which we should have a larger distances as we have an increase in magnitude to reach the values that we were given, R20, 70, etc. Because of the strength of magnitude, we would have to be at a farther distance to reach these values.